Development Pharmaceuticals in association with Higher Secondary Principals Forum.
Namaskar, hello viewers, and you my dear friends, students. Today we are going to do a session on current electricity. We are going to explore concepts under branch of physics called current electricity. But before we start that, let me go through the chapter 2 which we have done in previous session. In chapter 2, that is electric potential and capacitance, we have discussed about the concept of potential difference. Potential. Then we have discussed what is called as potential energy of a dipole. Then electrostatic conditions of the conductor. And the last part, we have discussed what is called as electrical capacitance. Very important device we have learned in that particular part, that is capacitor, which is having a electrical capacitance or a capacity to hold charge, more or less. But what are the factors it depends upon, that we have discussed. Just like this capacitor, we are going to study a device called resistor in current electricity. More or less, we are going to incorporate this concept which we have studied in chapter 1 and chapter 2, in chapter 3 also. And taking this concept forward, we are going to learn what is called as current electricity. In chapter 1, you have seen if the charge, positive charge is there in electric field, it tries to move in the direction of electric field. Positive charge always moves in a direction of electric field. Negative charge try to move in direction opposite to the electric field. If this is the electric field direction, negative charge moves opposite to the direction of the electric field. Now question will arise in your mind. We cannot make a charge, negative charge to move in a direction of the electric field, which is usually moving in opposite to the field. Similar situation I'll tell you in 11th standard. If you want to make an object to go in the direction of the gravity, just leave it from some height. But if you want to throw it against the direction of the gravity, then you have to do some work. And that work done is then stored as an energy. It will rise to some height and then it will fall. Likewise, if I make minus q charge, fire minus q charge in a direction of the electric field, some distance it will travel, it will stop, and then again it will move against the direction of the electric field. Why I am telling you all this? Because this type of situation will help you to understand the concept which will be done in chapter number 3, that is current electricity. Now, current electricity is very important chapter. The first 2 chapters are having a concepts which are under the branch of physics called electrostatic, and current electricity is totally a different branch of physics. And this particular current electricity chapter, it's a focal point of 12th standard physics syllabus. Why I say this? Because of 3 reasons. First of all, it has maximum marks in the syllabus. Second, most of the concepts which are done in current electricity will be reflected in many subsequent chapters. Wherever you encounter a situation where charges will be in motion, you are going to use a concept of current electricity. And third reason why I say that this chapter is a focal point, third reason is, as a practical point of view, if you see most of the experiments based on this particular chapter. And that is the reason why I say this particular chapter, current electricity, is a focal point of standard 12th standard physics. So that's the reason it's a big chapter we are going to do in 2 parts. So part 1, I will be dealing in this particular session, and current electricity part 2 will be in another session. So fasten your seat belt, take paper, pen, and try to be attentive in this particular session to learn concepts under current electricity. So let's start. Now, what is meant by current? Current means flow of charge. In everyday life, you encounter so many situations where the charge flows. For example, lightning that comes straight away gushing towards the surface of the earth from the sky is in the form of flow of charge. Only thing is that charge flow is unsteady. We encounter so many other situations where the charge is steady. Now, for example, the circuits which we construct, simple circuits which we construct in the laboratory, few milliammeter, millivoltmeters, some resistor we connect, some elements we connect, those circuits will be having a steady currents. Just like what current flows, charges flows, water flows also gives rise to a water current. Now, for example, the water flowing from this container to this container, it will flow throughout this cross-section of the pipe connected between the two containers. So there is a water current here, water gushing out through the rivers, stream in the river basin. It's also, sometimes it is a steady flow, sometimes it is a different flow. So what exactly mean by the steady, unsteady flow of water that you have studied in 11th standard syllabus. So let's concentrate on flow of charge. So mostly we are going to deal about steady flow in this particular chapter. So second, we have to understand the direction of the current. What is the direction of the current usually taken? And conventionally, the direction of the current is taken to be opposite to the flow of electron. Now, for example, I have shown a current in this part of the segment. The current direction shown in the paper, shown in the diagram is this way, but actually the electrons are moving opposite to the flow of current. So the convention of the current is taken opposite to the flow of charges, opposite to the flow of electron. Then the current is a scalar quantity. What is meant by that? You can just add the current, 10 amp and 5 amp, you will get 15 amp. We don't use a principle of superposition to find out the resultant current as such. We just add current algebraically. Now, question will arise in your mind, current has a magnitude and it has a direction also, why it is not a vector quantity. Because of this reason, it don't follow the principle of superposition. Then the next important point is the charge is conserved. Amount of flow of charge is conserved. As much as current charge is entering one section, same amount of charge will leave from the other side of the section. So that makes the charge is conserved. Amount of flow of charge is conserved. So what is meant by current? Current is flow of charge. Now, these carriers of charges are different in different material. In the conductor, the flow of the carriers of current are electrons. In case of semiconductor, it's electron and hole, which you are going to all together study in chapter number 14, carrying 6 marks in your syllabus. And if it is the electrolyte, what is meant by electrolyte? Electrolyte means solution which conducts. Their ions are the carriers of the current. So these are the different carriers of the current which you have in different situations. If you take a gas also conduct at low pressure and high temperature. They also have ions and electrons as the carriers of current. So in this chapter, we are going to stick to steady flow of current. This steady flow of current will give rise to a magnetic field. That is the content of the next chapter. The unsteady flow also gives rise to a magnetic field. If the magnetic field changes and that produces the current, that is the content of the electromagnetic induction chapter. And if both they interact, there is a disturbance created that is called as electromagnetic wave. That is the content of electromagnetic wave chapter. So in this chapter, we are going to study steady flow of charge. Now, when I say the wire carries a current, what exactly mean by that? Now, if I take a conductor, the electrons are the carriers of current, I said. Now, when I say conductor, the electrons are free. These free electrons, especially the metals, they have plenty of free electrons. So these electrons are moving. Now, question will arise in your mind. This moving electron doesn't amount to current. this moving electron in the conductor, electrons are not at rest in the conductor. They don't amount to current. No, they don't amount to current. Why? The reason is these electrons are in random motion. They collide with the metal ions inside the conductor. They are in random motion. The net displacement of this electrons is zero, net current is zero. Now, detail about that we are going to learn in the topic ahead. So, let me tell you, in a conductor, when there is no potential differences applied, the electrons are in motion, but they are in random motion. Now, what exactly happens when potential difference is applied? Suppose we have this as a cross-section. This is a conductor. It's a part of the conductor. This is a part of the conductor. And imagine that in this conductor, there are plenty of electrons which are moving randomly, and net current is zero. Now, suppose I have positive charges here on this side, and negative charges are here on this side. Now, when I make positive charge this side and this side, immediately there is the electric field will be set in the conductor. Electric field will direct from positive to negative. So electron will start moving, and these positive charges will get neutralized. If all the charges are neutralized, that means there won't be any charges left here, the current will reduce to zero. But somehow, if we replenish these charges on this side, the electron motion in the conductor will go on. And that replenishing of the charges on the surface of the conductor is the job of a battery. And we say potential difference is applied. So when you apply a potential difference, what exactly happens is new charges are created. Electrons are different. Electrons from the low potential, they drift towards the higher potential, and that's what exactly the current is set in that conductor. Now, what is meant by current? We define a current as amount of charge that will flow through a given cross-section of the conductor. So, whatever is the amount of charge that flows through a given cross-section of the conductor, that is current. So, that's the reason we have current is charge upon time. And if you put charge is equal to NE, we get beautiful relation I is equal to NE upon T, where N is the number of electrons flowing through. And this formula we have taken up from the first chapter. Now, if the charge flow is not steady, unsteady, in that case, you take a small amount of charge, passes through small time interval dt, and charge that charge upon dt, dq upon dt will be the current. And we can say in mathematical term, current is a derivative of charge. And also, if you want to find out the average charge, then you can go for some different formula, integral of I dt. And if you try to plot a graph of current versus time, suppose this is an unsteady current, and if a graph is there, current versus time, and if you want to find out how much is the charge in time 2t second, then you can just find the area under this curve, area under that graph, and you will be able to find out total charge stored. Total charge passes through the given cross-section in that time. Unit of current is ampere, coulomb per second. It's a fundamental quantity. Ampere is a fundamental quantity, and milliamp, microamp. These are the smaller units. In everyday life, you encounter. Suppose if it is a simple circuits which you do in the laboratory, that more or less constitutes a current of few milliamp. A household current, 15 amp, 5 amp, 10 amp, that way. The current which is coming in the form of lightning is tens of thousands of magnitude. So very large current that is coming on the surface of the earth. So that's the example of different magnitude. You should learn magnitudes in physics, then only you understand physics well. Now, when I say current, the charges are in motion. That means wherever charges are in motion, it amounts to current. Let's see one of such example. Electron orbiting around the nucleus. Now, orbiting electron around the nucleus constitutes a current. And how much current that electron moving around the nucleus can constitute, that is given that one can find out in this particular example. So I straight away use a formula, current is equal to charge upon time. Charge of the electron is E. It is orbiting in the about a radius r. Centrally located proton is there, which is in the nucleus, and this is the hydrogen atom example I have taken. And if you take 1 by T as frequency, the current will be charge time frequency. So if the electron is gyrating at certain frequency, I can find out how much current it can constitute. So I is equal to E into nu. Nu is the frequency. And this is very important part as far as magnetism is concerned. And if you go in detail under magnetism chapter, this is the origin of magnetic property that you will learn in moving charges and magnetism chapter, and magnetism and matter chapter. Another example, you can take a charge is not charge going at particular charge at particular instant. You are asked to find out charge is given as a function of t. Just find out the derivative, substituted value of time, and you can easily find out how much is the current at that instant using this formula of dq upon dt. So this is more or less the examples which we can encounter. So as I said, the electrons in the conductor are not at rest. They are moving randomly anyhow, and net displacement, net current is 0. When the potential difference is applied between the ends of the conductor, I told you that the electric field sets up in the conductor from higher potential towards a lower potential, and electrons start drifting towards the higher potential. Now let's try to understand what is exactly meant by Ohm's law. What is the relation between the potential difference and the current? As I told you, what is current? Current is amount of charge that passes through a given cross-section of the conductor in given time. That ratio is called as current. That's the way we define current. Now, when I increase the potential difference, so I make this side more potential, higher potential. When I increase this, the amount of charge flowing through the conductor will increase. That means amount of charge passing through the given cross-section will increase, and thereby increases the current. So what does Ohm's law states? Potential difference is directly proportional to current, provided, please mind this, provided the physical condition, temperature, strain remains unchanged. So if you keep length, area of cross-section of the conductor constant, temperature surrounding the constant, if you keep this particular condition constant, then only the potential difference is directly proportional to current. And the proportionality constant that comes into play is nothing but the resistance of the conductor. Now, what is that resistance of the conductor? As I told you, electrons moving towards the higher potential, they are constantly colliding with the metal ion. They are not having a swift ride. They are colliding with the metal ion. They cannot move swiftly. That is what is the resistance amounts to. So that resistance is opposition to the current. So if this is the direction of the electric field, this is the direction of the conventional current, electrons are moving in this direction, drifting in this direction, they are colliding with the metal ions. Okay, now let's try to understand. So the formula we have, R is equal to V upon I, or V is equal to IR. We can now understand what are the factors on which this resistance depends. The first factor, it depends on the length of the conductor. If you increase the length of the conductor, the resistance of the conductor increases. Very simple to understand. If you increase the length of the conductor, electron find more atoms to collide on the way, and that's the reason the resistance is increasing. So resistance is directly proportional to the length. Second, resistance is inversely proportional to the area of cross-section. What does it mean? If I have a larger area, double the area. If you double the area, the resistance becomes half. If you make the area of cross-section half, the resistance will get double. One can easily prove this part, understand this part. So resistance is inversely proportional to area of cross-section. Thicker the wire, lesser is the resistance. And then if you compare these two equations, and you will find that resistance is some constant times L upon A. This constant is called as the resistivity of the conductor. And that resistivity is also known as specific resistance of a conductor. Now, what is the other? So resistance depends on length, resistance depends on area of cross-section. The proportionality constant which comes into play is called as resistivity of the conductor. It is also called as specific resistance. Now, the third factor on which the resistance depends is nature of the material. Copper, aluminum, any conductor, if you take of different material, its resistance will be different. It depends on temperature. So resistance can depend on length of the conductor, area of cross-section, nature, and the temperature of the temperature surrounding the conductor. Resistivity and resistance are two different things. Resistivity is a measure of ability of a conductor to oppose. It only depends on characteristic of a conductor and temperature surrounding the conductor. Please understand this difference. Resistance can depend on length, area of cross-section, temperature, nature. But resistivity depends on the material and the temperature. Now, for example, if I have wire of 1 meter, if you cut it into 2 parts, each part will have same resistivity. Their resistance will be different. Okay, so if you change the length of the given conductor, given material, its resistivity will remain same. That's what exactly it means. And the unit of resistivity is ohm meter, which can easily find out using this. So as I said, you cannot say resistance always equal to resistivity. Under certain condition, resistivity will be equal to resistance, provided you have length of the conductor exactly 1 meter and area of cross-section exactly 1 meter square. In everyday life, we don't find this type of conductor, where length is 1 meter and area of cross-section is 1 square meter. So resistivity is never equal to resistance. Only under this condition, it can become equal to resistivity. So resistivity of the material is also different material have different resistivity. Resistivity of the metals, more or less, if you try to see 10 raised to minus 8 ohm meter. Resistivity of insulators is very high. Semiconductors somewhat less resistivity. So resistivity of materials like metal is very, very less. Now, if you try to plot a graph of voltage versus current, you get a straight line, and we say that Ohm's law is verified. So conductors which obeys Ohm's law, they are called as ohmic conductors. And conductors don't obey Ohm's law, they are called as non-ohmic conductors. So potential difference is directly proportional to current under certain conditions. That is valid for certain conductors that will be called as ohmic conductors. Metals are ohmic conductors, whereas electrolyte, diode, gallium arsenide, these type of materials are they give non-linear graph. That's the reason they are called as non-ohmic conductors. So if you try to see the graph for a diode, for example, as a voltage increases, current increases proportionally. After some time it increases. You are going to witness this in one of the experiments under diode characteristics in the 12th standard syllabus. Then, if you try to see this particular element, this is a graph for element gallium arsenide. It shows a linear graph here, and then there's a non-linear region, and this is a negative resistance region where voltage increases, current is decreasing. That is a negative resistance region. So this is more or less the graphs for the ohmic conductors and non-ohmic conductors. So these are the limitations on. There is a limitation on Ohm's law. Now, here if you see this particular graph, this particular dotted lines means perfect conductor obeying Ohm's law. And this X is any other conductor. Y and Z are more or less deviating from the standard one. You can easily say that X is the best ohmic conductor compared to Y and Z. And at higher temperature, if you see, they are deviating away from the linear graph. What is the reason behind that? And the reason behind that goes back to resistance conductor depending on temperature. So as you increase more current, the conductor gets heated. The electron collide more with the metal ion, and that's the reason why the resistance the linear graph of V by I deviates from the standard one. So that temperature dependence we are going to study in the topic ahead. So this is what exactly meant by ohmic conductors and non-ohmic conductors. Now, let's learn the concept of what is called as drift velocity. What exactly happening inside the conductor? As I told you, before applying a potential difference, electrons are in motion, but they are randomly colliding with the random motion it is, they are colliding with the metal ions. This is a blue regions which they are shown as a metal ions. Then the electrons are colliding less number in case of good conductors, and poor conductors they collide more. So this is more or less the situation in a conductor when no potential difference is applied. But when the potential difference is applied, what happens? The speed of the electron is more or less 10 raised to 5 meters per second, 10 raised to 5, 10 raised to 6 meters per second, very large speed. So with that large speed, they collide. Now, for example, this blue path which is shown is the collision which is experienced by the electron when no potential difference is applied. So electron travels, here there is a collision, it drifts this way. Here there is a collision, it gets this way. Here there is a collision, it gets this way. Here there is an ion to which it collides, it comes this way, this way, this way. This is the blue path which is shown. This blue path which is shown is the trajectory of the electron in absence of electric field. And trajectory is almost straight in absence of electric field. In presence of electric field, what exactly happens? When the electric field is applied, electron drift against the direction of the electric field, I told you. So this is more or less the trajectory which they follow, dotted line trajectory they follow, and there is a net displacement B to B dash in presence of electric field. And do you know what is the drift velocity comes out to be? Drift velocity comes out to be just 10 raised to minus 4. The drift velocity is very, very less. It is very, very less drift velocity. One can calculate this drift velocity. So this is the concept more or less of the drift velocity. So what is drift velocity we are going to define now. This is what is happening inside the conductor. So let's define now what is meant by drift velocity. We'll calculate we can come out with the formula for this drift velocity, and then we can define one more concept based on this. So what is drift velocity? How we can find out? So drift velocity we have to define as average velocity. Why I say average velocity? Because electrons are colliding, they have some velocity, they collide, they have different velocity, they have different velocity. So after each collision, the successive collision, the velocity changes. So average velocity of the electron in the direction against the electric field, that is called as drift velocity. Now, this average velocity we can find out by simply taking the force acting on the charge of an electron. Minus E is the charge of the electron. Force is minus EE. And if I use a formula, acceleration is force upon mass minus EE upon m is the acceleration. And velocity is nothing but the acceleration into time. Now, here that time is called as relaxation time. Why we call relaxation time as the average time between the two successive collisions? What is meant by this statement? What is meant by relaxation time? Relaxation time means average time between two successive collisions. So if you see, suppose the electron have collided here and move on to this point. So here it takes more time. Here it takes less time. Here it takes more time. So average time you take, that is relaxation time. And that relaxation time is denoted as tau. And you can easily come out with the formula minus EEM into tau. We can calculate this drift velocity, and it is very much 10 raised to order of 10 raised to minus 4 to 10 raised to minus 6 meters per second. So drift velocity is very, very less when the electric field set up in the conductor. So question will arise in your mind, if drift velocity is so less, then when you put on the switch, why the current is established immediately? What is the reason behind that? What exactly is the reason behind it? When you put on the switch, you get a current established in the circuit immediately. The reason is, it's not that electrons have to travel all the way from lower potential to higher potential to constitute current. Remember, my dear student, it is not electrons have to travel all the way. Once the electric field sets in, the electrical impulse will travel at the speed of light and current is established. And that's the reason why you will get the current established. When you put on the switch, the current flows immediately. It's an electrical signal which travels at speed of light. So this is the concept of drift velocity, relaxation time, and that's what exactly you should know. Then, now let's try to understand the relation between current density, conductivity, and electric field. These are the related concepts which you should know. Now, current density is nothing but current per unit area. Current per unit area. As I told you, electrons are in motion in presence of electric field. They don't travel in a straight line as such. They do collide, but there is a net displacement against the direction of the electric field. And that's the reason it results into drift velocity. So net drift velocity always superpose in the direction against the direction of the electric field. Now current density J is I upon A. If I put V is equal to IR, I is the current, R is rho L by A. Rho is the resistivity which we already studied before. J is I upon A. V is equal to EL. EL is nothing but potential difference between the ends of the conductor is electric field times the distance between the two length of the conductor, that is E into L. If you substitute this, you will get electric field is J into rho. Current density J will be equal to sigma into E, and sigma is called as conductivity, which is a reciprocal of resistivity. If conductivity is high, resistivity is low. If resistivity is high, conductivity is low. That's what you can understand here. And let me tell you, my dear friends, current density is a vector quantity. Current is a scalar quantity, current density is a vector quantity. And one can write this as J bar into sigma into E bar. Now, always the current density is measured always perpendicular to the cross-section of the conductor. The flow should be normal to the cross-section of the conductor. So if I take a cross-section slightly slanting, if I take this cross-section slightly slanting, then we have to take more or less this particular direction. Normal to the surface is the direction. The component of this area vector will be along this, which is dA cos theta. In that case, the current density become J is equal to I upon A cos theta. So A cos theta is the component along this. So in that case, you have to take it A cos theta. If you choose area of cross-section slanting this way, if you plot a graph of J versus E, you will get a straight line. X will have higher conductivity, Y will have lower conductivity, because slope of this graph will give you the conductivity. So sigma is the conductivity. It's 1 upon reciprocal of resistivity. Resistivity has a unit ohm meter. Conductivity will have a unit ohm meter inverse. So that is the unit of conductivity. So we have discussed what is drift velocity. Drift velocity is the average velocity of the electrons moving from lower potential towards the higher potential in presence of electric field against the direction of the electric field. Relaxation time is the average time between successive collision. That is called as relaxation time, and it is denoted by tau. Now, let me recall, electrons in the conductor, they move from lower potential towards the higher potential. They collide with the metal ion. Number of collisions they experience with the metal ion, and that's the reason their motion is retarded. Now, electrons are colliding with the metal ion. That's amount to a resistance we have studied. Now, let's try to write a relation, derive a relation between current, drift velocity, and the current. What exactly the relation between drift velocity and the current? So, as I told you, drift velocity is the average velocity. We denote that by Vd. So, Vd is the drift velocity. So, we denote drift velocity by Vd. Now, suppose this is a conductor, cross section of the conductor. A is the area of conductor. A is the area of conductor. L is the length of the conductor. What will be the volume of this conductor? Area into length will be the volume of the conductor. Now, suppose there are n number of electrons in unit volume, per unit volume. Small n is the number of electrons per unit volume. Then in this volume of Al, there will be NaL electrons. NaL electrons will be there in this cross section of the conductor, in this volume. Now, if I take a charge of the electron as E, then total charge that is flowing in this through this conductor in time t second is nothing but NaLe. And we use a formula of the current. Current is equal to charge upon time, NaLe upon time. Time I can write as length upon velocity. Substitute that, you will get this beautiful relation I is equal to NaEVd, where N is the number of electrons per unit volume, A is the area of cross section of the conductor, E is the charge of an electron, Vd is the drift velocity. Now, if you substitute drift velocity as minus E upon m into tau, then you will get this relation. We can find out the current density from that. Current density will be this relation. And we define one more quantity called mobility. And the mobility is nothing but the magnitude of drift velocity divided by electric field. Mobility more or less is expressed to what extent those charges are mobile in nature. So, mobility is Vd upon E. Now, electrons are the carriers of current in the conductor. Its mobility is different. Semiconductors, electrons and holes are there. Its mobility is different. Ions' mobility is different in the solutions. So, solution, there are ions which are moving. So, mobility is different in different situation, in different carriers, in different situation. So, that is what is called as mobility. Now, let's also try to understand what is the relation between electron density, resistivity, and relaxation time. Now, this particular relation you have to write and see. Piece of paper, you have to practice it and resort to the final formula. The formula which is very important is I is equal to NaEVd. This formula you have to remember. Likewise, another formula which you have to remember, which will help you to solve MCQs coming in the MCQ level test. So, if you want to find out the relation between electron density, resistivity, and relaxation time, so take a formula for drift velocity. Current is equal to NeAVd. In place of Vd, I can substitute EV upon m into tau. But this V, electric field is nothing but V upon L. That you substitute, you get this formula, and V upon I is the resistance. Resistance is rho L upon A. L and by A cancels, and you get resistivity as m upon Ne square tau. What does this mean? That means resistivity is depending on mass of the electron. Number of resistivity is inversely proportional to relaxation time. Mass of the electron is constant. N is the number of electron per unit volume. So, if the number density of electron changes, resistivity can change. So, resistivity is particular to the characteristic of material I told you. What is meant by that characteristic of the material? The number of electrons per unit volume of that material changes, then resistivity can change. E is the charge of an electron, which is 1.6 into 10 raised to minus 19 coulomb. M is the mass of the electron, which is 9.1 into 10 raised to minus 31 kg. And tau is the relaxation time. So, what does really means? Resistivity is inversely proportional to relaxation time. What is relaxation time? Average time between the successive collision. So if the resistivity is more, relaxation time is less. There will be a frequent collision. So time is less, there will be a frequent collision. So if the resistivity is more, relaxation time is less. So understand this based on how exactly the things are happening inside the conductor. One cannot photograph it, but one can easily understand if you go in detail of this. So that's what the relation between resistivity and the relaxation time. That's a beautiful concept of resistivity and relaxation time. Next, we have what is called as temperature coefficient of resistivity. Now, I told you, we have discussed earlier that potential difference is directly proportional to current flowing through the conductor, provided physical condition remains constant. And one of the physical condition which I have mentioned is nothing but the temperature. So if the temperature surrounding the conductor changes, what is the effect on resistivity? As I told you, resistivity is depending on relaxation time and number of electrons per unit volume. So when you increase the temperature, what exactly is the situation in the conductor? Electrons are colliding with the metal ions, but when the temperature is increased, the metal ions vibrate about their mean position. So metal ion vibrate about their mean position, and naturally these electrons will suffer more collision with the metal ion. So since the collision with the metal ions frequently increases, relaxation time decreases. So as the temperature increases, resistivity changes, resistivity increases. Measure of this change of resistivity is the temperature coefficient of resistivity. Just like to what extent light is bending in the denser medium, that is given by refractive index, measure of refraction. Just like if you supply heat to the conductor, it expands. To what extent it expands, that measure is given by coefficient of linear expansion. Likewise, we have what is called as temperature coefficient of resistivity, and that is nothing but it gives you to what extent the resistivity changes with temperature. So if we have resistivity, say rho 0 initially at temperature say T0, initial temperature, and final resistivity at temperature is T, change in temperature, change in resistivity will be rho minus rho 0. Change in temperature is T minus T0. This ratio is called as temperature coefficient of resistivity. Temperature coefficient of resistivity. Okay. And from this, you will come to know the unit of this. This is ohm meter. This is ohm meter. The unit of this that prevails, and the unit is per degree centigrade, or degree per degree Kelvin. You can state that as a unit of temperature coefficient of resistivity. So temperature coefficient of resistivity gives a measure of resistivity change during that particular increase in temperature. If the change in resistivity is more, alpha, this is denoted as alpha, the alpha is the temperature coefficient of resistivity will be more. Likewise, I can say temperature coefficient of resistance. So R, I can write same formula as rho is equal to rho 0 1 plus alpha T minus T0, or I can write it for resistance. So as the temperature increases, resistivity changes. For conductors, resistivity increases. For semiconductors, resistivity decreases. And if you try to find out the slope of resistivity with temperature graph, the slope of this will give you alpha value. So if alpha is high, that means resistivity or resistance of that material is changing more. If alpha is less, means that material change resistance is less. Now, when you make a resistances out of wire, we have to choose a certain material of which the resistance should not change much. In that case, we choose a material which have very low value of alpha, and we preferably choose what are called as constantan and manganese, because it has very low of temperature coefficient of resistivity. Alpha is positive for metal because as the temperature rises, resistivity rises. Alpha is negative for semiconductor because as the temperature rises, resistivity decreases, conductivity increases. Semiconductors become more and more conducting when temperature is increased. Remember this, and you are going to study this in chapter number 14, semiconductor devices. Okay, so in insulators, number of electrons and semiconductors, number of electrons per unit volume increases with the temperature, resistivity decreases with temperature. That's what you should know under temperature coefficient of resistivity. So in the nutshell, what is meant by temperature coefficient of resistivity? If the change in resistivity is more with rise in temperature, temperature coefficient of resistivity is more. That's what it means. Next, we understand what is meant by resistor. We have discussed temperature coefficient of resistivity, what is meant by resistance, what is the cause of resistance. Cause of resistance is nothing but electron colliding with the metal ions. And now we'll see the element called resistor, types of resistances. There are various types of resistors. Wire-bound resistor and carbon resistor, which are mainly used. Wire-bound resistors are nothing but made up of wire, especially the wire which is chosen is manganese or constantan or nichrome. Why constantan and manganese is preferred? I have told you the temperature coefficient of resistivity is very less. And carbon resistor, we have, these are made up of mixture of carbon black and clay and resin binder. This particular carbon resistors are very compact, cheap, and they are widely used in electronic circuit. So these are the resistors which are available if you want to construct an electronic circuit. Now, what is the job of resistor? Resistor job is to oppose the current in that particular circuit element, to lessen the current in that particular circuit element. Now, how the value of the resistor is estimated? Let's try to understand that. And the value of the resistor is estimated more or less using what is called as color codes. So we have here wire-bound resistors shown here. Here there are carbon resistors shown, and these carbon resistors are having beautiful colors on the body. 3 colors are very close together, and the 4th color is away from the 3 colors. So likewise you can see here. Now how exactly one can find the value of the resistor using this color code? So we have what is called, the colors are like this: black, brown, red, orange, yellow, green, blue, violet, gray, and white. They are assigned certain digits. The first band will represent, say, any of this color. That band digit will be assigned. Second band will give you the second digit involved in the number, and the third band will give you the multiplier to the base 10. So, and the 4th color is, say, gold or silver or no color there. Then in that case we take a tolerance. Tolerance will help you to find out the range of the resistance of the resistor. So if the 4th color is gold, the tolerance is about 5%. Silver, it is 10%, and no color means 20%. Now just looking at this won't help. We'll actually find out the value of resistor doing some calculation. So let's do some calculation. Yes, so let's work out some example. Suppose we have a resistor here, and there are three bands are like this. First is, say, brown, second is, say, black, and third is, say, red, and 4th color is, say, silver. This is the color code which you have to by heart. You should remember it. So B means for black, first blackout. Second B is for brown, red, orange, yellow, G for green. First G comes for green, B for blue, V for violet, G for gray here, and last color is white. So if the first band is brown, the first digit will be 1, brown is 1, Black is 0. Black is 0 into third color gives a multiplier to the base 10. Red here is 2, 10 raised to 2. This is the value of the resistor. And if fourth color is silver, it will be 10% plus or minus 10%. This is the value of the resistor. We can find the 10% of this, add to that this value, you will get one value. If you subtract 10%, you will get another value, you will get the range of resistance. So this is the way one can calculate the value of the resistor. And you have to by heart this particular code. How to remember this code? There are methods to remember this also. You just remember this code by making a phrase out of it. And the popular phrase which we see in the book also, that is B.B. Roy of Great Britain having very good wife. This is the phrase we use to remember this particular code. B.B. Roy of Great Britain having very good wife. So this phrase you can use. You can use another phrase, better buy resistances, otherwise your agreed bias voltage go wrong. So you can use that also. But this is most convenient way of remembering this particular resistance color code. And you remember the tolerance as well. So this is the way you can solve many examples based on this. Yes, next thing we'll go through what is called as combination of resistances or combination of resistors. The symbol for resistance is this. This is a symbol for resistance. So if the number of resistances are connected in series, how one can find out their combined resistance, how one can find out their equivalent resistance, that we can do it very easily. If three resistances R1, R2, R3 are connected in series, across them is the potential difference V with the help of this battery plug key emitter. You can neglect the resistance of this emitter, neglect the resistance of this battery, and there is a potential difference V across it. This will send a common current through these three resistances. So current is common, potential drop across them by using Ohm's law relation, V1 will be equal to I times R1, V2 will potential drop across this, V2 is equal to I times R2, V3 is equal to I times R3. Total potential drop gets divided among this R1, R2 and R3. So total potential drop is V1, V2 and V plus V3. If you, in place of these three resistances, if you have one resistance which is called as equivalent resistance, RS I'll denote, in that case you substitute in this equation and you will get total resistance as R1 plus R2 plus R3. So if you put the resistances in series, you have to just add all the resistances value to get total resistance. And if you try to see that all the resistances are same, then you can find out the resistance N times R. The underlying point which you have to remember is if they are connected in series, the current is common flowing through them. If the resistances are in parallel, let's try to work out this part also. So R1, R2, R3, three resistances connected in parallel. Now, they are connected between two common points, X and Y. So potential difference across each one of them is same. Please understand this part. Potential difference between X and Y is same. Current is flowing on account of this battery, plug key and emitter here. Emitter measures current, and this current gets divided into three branches, I1, I2, I3. So total current, I is equal to I1 plus I2 plus I3. Put using Ohm's law this relation, and we can resort to the final formula. 1 upon R equivalent is nothing but 1 upon R1 plus 1 upon R2 plus 1 upon R3. You can easily resort to this particular equation. So if you connect resistances in parallel, the reciprocal of equivalent resistance is equal to sum of the reciprocal of individual resistances. So from both these section, you can easily understand, if you want to add resistance, you put them in series. If you want to decrease resistance, you put them in parallel. In series, current is common. In parallel, voltage is common. So let's go through these some examples where these resistance are connected in series, current is common, this resistance, current is again divided into two branches. Here, all the three are in parallel, so current is here getting divided into three branches, and again it will meet into a main current. This current is divided into these two branches. Here same current is flowing, so R2 and R3 will be in series. Will be parallel with respect to that. So these hints will help you to solve some problems. There is also, these are the chains. It looks like a parallel connection, but it is a series connection. Same current is flowing. Here, parallel connection because they are connected between two common points. Another concept which you should know is resistance per unit length. And resistance per unit length is nothing but the resistance divided by length of the conductor. Suppose you have a wire of 1 meter. You find the resistance, say 2 ohm. 2 divided by 1 meter, that will be 2 divided by 1 meter, or 2 divided by 100 centimeter, that will be the resistance per unit length which you can find out. Per centimeter you can find out. So this is what is the concept of resistance per unit length. So let's solve some example based on this, and then you can understand better. Now, here, this particular circuit looks very complicated, but you can easily understand this. If you want to find out the equivalent resistance between A and B, you see, first try to understand through this 3 ohm and 3 ohm, same current is flowing, so it becomes 6 ohm. That 6 ohm, in parallel with this, it becomes 1 by 6, that will be 3 ohm again. This 3 ohm and this 3 ohm in series, 6 ohm, this 6 ohm and this 6 ohm in parallel. You can go on doing like this, and you can easily find out the equivalent resistance between A and B. So we'll actually solve some circuits based on this to understand most of the circuits. Some more examples I can take. Suppose I want to find out the equivalent resistance between A and B. You can take this 3 in parallel, this 6 resistance in parallel, find out their equivalent. This 3 in parallel, find out their equivalent. Then this sum what you will get, this sum what you will get, this sum what you will get will be in series. So that will be the total resistance between A and B. See this particular example, which is almost solved, not by taking the value, but you can understand how to solve. This is suppose a circuit. Now if you want to find out the equivalent resistance of this particular circuit, if you want to find out the current in the circuit, main current in the circuit, then you can solve this circuit. You take these 3 resistances in parallel, find out their value. Take these 2 resistances in parallel, find out their value. This is the equivalent circuit now. This and this is in series. You will get equivalent resistance here. This value and this will be in parallel. That combination is in series with this. And finally, you can get an equivalent resistance between these 2 ends. And if you know the voltage, if you know this equivalent resistance, easily you can find out the main current. Likewise, this example, start from here, solve this, resort up to this, and you can find out what is called as main current flowing through the circuit. So these are the beautiful examples one can solve based on this. Then, in this case, we have plenty of examples here. We can easily find out how to find out current flowing. In this case, for example, if 10 volt, start solving the simplest situation first. Then you can solve more situations. Now, simplest situation, plus 10 volt, minus 10 volt, current flows, we can find out. Potential difference will be 10, minus of minus 10 will be 20 volt, 20 divided by 20, it will be 1 amp. So this current will be 1 amp. Likewise, you can find out what is the potential at this point using the same formula. VA minus VB is potential difference is equal to current into resistance. Current and resistance is given, find out that. If the current is flowing in these 2, how exactly find the value of R? If the current is I1 and I2, how one can find out the resistance? How one can find out this current? If these 2 things are given, if you are asked to find out the potential difference between this end and this point, you can find out the main current first by using equivalent resistance of this, and then find the potential difference between this and between this also. Then if you ask to find out in this circuit, this becomes now more complicated. So if you want to find out the potential difference between C and D, then find the potential difference between A and C. find the potential difference between A and D, and then potential difference between C and D will be potential difference between A and C minus potential difference between A and D. So this you need to solve, you need to practice. Okay? So this type of situation you can practice, go in detail of this. Sky is the limit to solve numericals based on this part. So let's solve some situation based on this before we go ahead. Let's see this particular example. Actually, we'll do it. So start drawing this circuit and try to solve this. Let's solve together. So we have to find out equivalent resistance between A and B. So how to get equivalent circuit out of this? Let's start from there. You put this point, they say C, this is D, this is say E, this is say F. So C, D, E, F. This is F. Okay? Let me start from this point. From A to C, I have one resistance. From C to D, I have another resistance. This is 1 ohm. This is 3 ohm. From D to E, there is another resistance. This is E. But E is connected to C. E is connected to C. E is connected to C. From E, there is another resistance of 3 ohm. This is 3 ohm. This is 3 ohm. This is F. From F, there is another resistance. And this is D. So this is the equivalent circuit of this little bit complicated circuit. Not so complicated, but little bit complicated. First take up simple one and then go for the difficult one. Now it is very much evident from this 3 ohm, 3 ohm, 3 ohm are in parallel. So you can easily find out 1 by 3 plus 1 by 3 plus 1 by 3, 3 by 3, 1. So this resistance will be 1 ohm. This resistance is 1 ohm. And this resistance is 5 ohm. So naturally the equivalent resistance between A and B, equivalent resistance between A and B, 1 plus 1 plus 5, that is 7 ohm. So that's the way we can solve this type of circuits. So go take up this type of network and go through this type of network more or less based on this part. Another example, let me take, this is one example. Let me take another example, example number 2. Suppose we have a circuit like this. One can easily find equivalent resistance between A and B. How to find out? This is given as 1 ohm. This is given as 1 ohm. This is given as 3 ohm, say. This is 4 ohm. This is 2 ohm. This is 2 ohm. This is 4 ohm. This is 2 ohm, suppose. And this is, say, 1 ohm again. Okay? How to start with? First find out the equivalent resistance between if I pass the same current here, this current get divided into 3 branches. The same current will flow through this. These and this will be in series. So you will get one resistance. I will reduce this circuit. I won't draw it again. So I will reduce this circuit. This becomes 4 ohm now. This will be 4 ohm now. This 4 ohm and this 4 ohm in parallel, 1 by 4, 1 by 4. It will be 2 by 4. 1 by 4 plus 1 by 4, it will be 2 by 4. Equivalent resistance will be 4 by 2. So resistance will be 2 ohm. So out of this you will get 2 ohm. Out of this you will get 2 ohm more or less. This 2 ohm and this 2 ohm are in series. You will get 4 ohm. That 4 ohm and 2 ohm in parallel, that you solve. You will get net resistance here. And finally, you add up these resistances, you will get final resistance. You can come out with the final answer, the resistance between A and B. So this way you can solve number of numerical based on this. Then, another example let me take. Suppose you have 2 loops like this. We have 2 loops like this. They are just connected here, just connected here. These are the two loops which I had shown in the circuit in the PPT. Now, suppose this radius is given as 2 meters, say, and the resistance of this given as 1 by pi ohm per centimeter. This is the resistance given. And this is given as 2 centimeters. The radius is given as 2 centimeters. One can find the equivalent resistance between A and B. First, find the resistance of this circular loop. Circular loop will have length 2 pi r. So length is 2 pi r, and its resistance is 1 by pi. So resistance of the circular loop will be pi get cancelled, and it will be 2r. R is 2 centimeters. Centimeters get cancelled, and it will be 4 ohm. So this particular loop is 4 ohm. This particular loop is 4 ohm. Naturally, the total resistance will be 8 ohm, isn't it? No, it's not 8 ohm. You have to take this part as a half resistance, this part as a half resistance. So total resistance is 4 ohm. You can take this 2 ohm, this 2 ohm, this 2 ohm, this 2 ohm, and so on. Provided it is connected at one single point, more or less touching. So these examples you can go through, number of examples are there. You can go through this and understand the concepts of resistances in series and resistances parallel. Now, let's go through the graphs that comes under this particular chapter. There are various graphs that could be understood in this particular chapter. Let's take up those some graphs to understand the concepts. Okay? So, the first graph which you must have encountered, so various graphs in this chapter. The first graph which you must have encountered, voltage versus current. If this is the line, if you try to find out the slope of this, you will get the slope as a resistance. And you can find out slope as the change in voltage, delta V, change in current, change in voltage upon change in current. Now, the slope is the resistance. So if I have two conductors, V versus I, there are two conductors. This is suppose X, this is Y, of same material, two different conductors. Which conductor has a greater resistance, one can find out by using simple situation like this. By finding the slope of, you take the formula R is equal to V upon I. We can do it in three ways. First way, I can take this I common. If I take I common, resistance is directly proportional to V. So whichever has V more, that particular conductor will have more resistance. So Rx will be greater than Ry. Another way we can do straight away comparing the slope. So slope of X is greater than slope of Y. And third, if you are given an angle, this is the angle given, then tan of theta is also delta V upon delta I. You can compare the resistances by finding the angle. Now, for example, suppose we have situation like this, where this is given as 30 degree and this is given as 60 degree, which has a greater, this is suppose P, which has a greater resistance. We can compare tan theta value and resort to the answer if it is a VI graph. If it is a IV graph, then this becomes 1 by, the resistance will become 1 by slope, and accordingly you have to infer which has a greater slope, whichever has a greater slope have lesser resistance. So these are the graph based on V is equal to IR. Likewise, we can have graph based on R is equal to rho L by A. This is another formula on which plenty of graphs could be plotted. One can plot a graph of V versus I, and you have suppose two different, both the materials are say copper, you are keeping resistivity L, resistivity A constant. Which material, which graph or which resistor have greater value of length? So resistance is directly proportional to length. So length of x will be greater than length of y. You can infer this. If you keep rho length constant, rho and L constant, in that case you can find out area of cross section of x. R is inversely proportional to area. So whichever has greater resistance, so area of cross section of x will be less than area of cross section of y. Whichever has greater resistance will have lesser area of cross section. Then if you have another graph where you have V versus I, and you have same conductor heated at two different temperatures. Same conductor heated at two different temperatures. Which temperature is higher? So you can easily find out T1 is greater than T2. Simple reason, as the temperature increases, resistance increases. So this resistance is more, for this slope is more, this resistance is less, slope is less, so temperature will be higher, T1 greater than T2. Likewise, you can also plot a graph on resistivity and length. So if you plot a graph of resistivity with length, it does not change with length. Same graph is for resistivity and area of cross section. It is not depending on area of cross section. We can also compare temperature coefficient of resistivity. Suppose we have two graphs like this. Which material has a greater temperature coefficient of resistivity? So slope of this is more, slope of A is more, then slope of B. So resistivity temperature coefficient of A will be greater than temperature coefficient of B. So these are the various types of graphs you can understand. Likewise, you can have a graph also where you can have a negative resistance. So in which region there is a negative resistance? Negative resistance. So as a voltage, we can take up voltage versus current or current versus voltage. As the voltage increases, resistance is decreasing. Or you can take V versus I also and infer in which region the resistance is negative. So these are the various types of graphs involved in this particular chapter. So go step by step, learn the concept, go through the graphs, learn the basics to solve the numericals. That will help you to understand this particular chapter. In the nutshell, let me tell you, when the conductor is there, in the conductor, electrons are in motion, but they don't amount to current. They are in motion, random motion, they doesn't amount to current. Once the potential difference is applied, electric field sets up in the conductor, electron moves towards the higher potential in the presence of electric field. It's not a regular motion as such. They collide with the metal ion. In presence of electric field, the trajectory between the two successive collision is curved, where in absence of electric field, it is straight line. Then electron drift towards the higher potential and don't need all the electrons from low potential to higher potential to go. Immediately when the electric field is set up, the electric current is established in the conductor. So that's what exactly is the concept of electric current. So you must have understood little part of this. NCERT's book have given clearly, you read that textbook part, chapter 3 very well. And if you go in detail of that, you will able to understand current electricity well. Of course, you have to refer other books also to solve numerical based on this. So I hope you must have enjoyed learning current electricity. I am enjoying this. I have enjoyed this teaching you current electricity part 1. You also do enjoy. See that you go through the concept, and don't forget my punchline. Physics is full of beautiful diagrams, handsome derivation, gorgeous concept, awesome explanation, and mind-blowing problems. Thank you. Don't forget to listen to my part 2 based on this current electricity. Thank you.
Prudent Scholars, powered by Lupin Pharmaceuticals.